Is this working? Yeah. Hi everyone, welcome to the first session of the afternoon. First up, we're going to be hearing from Raul-Martin Rebane, who's going to be talking to us about ZK-SecreC. I may have pronounced that wrong. Please take the stage.
I'm Raul-Martin from Cybernetica, and I'm here to talk to you about our language, ZK-SecreC, which is just to create zero-knowledge proofs. So the first question you might ask is why? And the answer is, well, we believe that zero-knowledge is a tool that can be used in a lot of different situations. So we're looking beyond like the blockchain industry as well, and we want to create really we want to be able to facilitate really big proofs for industrial applications as well. And in order to do that, the creation of zero-knowledge proofs has to be easy. So we want to be able to go to somebody and say, hey, we think zero-knowledge is a really good idea here, and this is how you can create that. And for normal languages, zero-knowledge has a lot of issues. So for example, one thing is that to keep track of on and off circuit variables is difficult, and also there's the witness expansion side channel, for example. So for many functions, you may not want to compute the function on the circuit. You want to just compute it kind of in your head and put the answer on the circuit and then run the inverse of the function on the circuit instead, because that's more efficient. However, by doing that, if you do it conditionally or in an inappropriate way, you're effectively creating a side channel. And in order to check that you're not leaking information through that requires a certain mechanism, which we have. So that is why we have created ZK-SecreC. We are, again, aiming at big data sizes, formats that are used in real life, and we're trying to kind of minimize the concessions that sometimes have to be made for things to work in zero knowledge. We want to be able to use the things that are just used in industry already, and be able to use that in zero knowledge as well. To handle the problem of whether something is on or off circuit, we have information flow labels, and we actually give the programmer a lot of granularity in what is on the circuit, what is not, also what is visible to only the prover, and what is visible in public. So for example, with loops, sometimes you have languages where the loop iteration must be constant at compile time. We don't have that. We have that just a restriction that the loop iteration amount must be public, and this is because it affects the shape of the circuit, which in turn is a side channel for how many iterations there are. Yeah, and so here you see that we have a effectively three-dimensional type system, where first you have the unqualified type. So this is just int, bool, string. Then you have the stage, whether it is off or on the circuit. And then you have the domain of the privacy domain, which is like, it belongs to the prover, verifier, or is it public? And so we give a lot of granularity, and we try to make it not messy by giving you also a high degree of polymorphism. So you are allowed to be polymorphic over the modulus, over the stage, over the domain. And you can also even branch on the stage and on the domain. So for example, here I have a bit of code from the standard library. So this calculates the square root for a fixed point number. Can you see my cursor? Yes, wonderful. So here you can see we are polymorphic over the prime. We are polymorphic over the stage and over the domain. And we have a fixed point number, which is for a given prime, stage, and domain, gets another fixed point number, which is of the same prime, stage, and domain. Here we do a branching, where we check if we're dealing with on-circuit or off-circuit computation. So off-circuit, we just calculate the value and we just give it as an answer. On circuit, we take the input, we take it off circuit, calculate the value, and then put the answer onto the circuit as well. But because we've done this computation in our head effectively, we also need to check if the answer that the prover, for example, put on the circuit is correct or not. So there are additional checks only if the domain is the prover domain. If it's in the verifier domain, we don't need to do that. So here you see everything that I mentioned. You see the polymorphism, you see the witness expansion, you see branching on both stage and domain, and in the end we have like a nice simple function where you just call square root fixed on a fixed point number and you get the answer. So our standard library has been growing through our efforts of creating real world use cases. So we want like very fixed, very realistic scenarios, right? We want to be able to achieve that, and by doing that, we've created like this this toolkit which already includes signing, hashing, fractional numbers, so all the both floating point, fixed point, and rational numbers. We have finite automata, and we have parsing. Parsing is especially important because often you're doing this proof on signed data, and you're receiving signed data, but you don't have any control over what the shape of that data is. So you will always need to do like a lot of parsing in real-world applications. As an example of this use case, we have the medical checks use case, and here we have this potential recruit who wants to prove to a military entrance processing station that they don't have any disqualifying conditions. This is actually very similar to the use case that Ron Canetti on the first day mentioned in the panel, right? Why would I need to show an insurance agency my entire medical records to show that I don't have like a condition or something? So here, the recruit sends requests to the medical providers that they use, and they receive signed medical records. Here, the military entrance processing station has a public list of healthcare providers that they accept, and they're public keys. And they also have a list of disqualifying conditions. And once the recruit has their signed data, they can run a zero-knowledge proof on which states that each diagnosis that they have is signed by a trusted medical authority, and all of these diagnoses are non-disqualifying. If they do have a disqualifying condition, there's also a mechanism for them to kind of reveal what they have, and then also claim that, okay, I have this thing, but nothing else, right? So there's like a little bit of extra there. And this use case has been extremely helpful for us because it has a lot of like little subtasks which have been really important for us. So for example, it runs on multiple fields, which is something that the backends, for example, have been really interested in. We have signature checks, we have hashing, we have string prefix checks, we have JSON parsing because the information that comes from the medical providers is in JSON, so we have to do like the JSON parsing on the assigned data. And yeah, it's been great, and every use case that we build gives us a little bit of more in our toolbox. So performance-wise, we have that for a single provider with 4 diagnosis per provider and 1,000 trusted providers in bad diagnoses, the circuit compile time is 23 seconds. This is only the circuit compile time. This is not with the backend. If you add the backend to it, this can increase by maybe a factor of 2 at most. It's not like very. It's not terribly significant, and also the numbers are always coming down, both on the backend side and on our side. So the reason you might think that this table is kind of funny and that all the circuit compile time and sizes are very similar, this is because this is the numbers I had from what is our fixed test case, and these numbers have all come down by 4 orders of magnitude. So they used to be more spread apart, and now they're just kind of converging, and they'll continue to converge because we have a couple of need improvements coming as well. Yeah, so this is how our pipeline works. So first the program writes in ZK-SecreC, and this gets fed to the ZK-SecreC compiler, which does all the type checking, the effect checking, and then transpiles it to Rust. This transpiled Rust interfaces with our static built-in library, which is kind of like this middleware. And here the built-ins interface with the backend, and this is where standardization is actually really important. Jonathan correctly pointed out that within the DARPA program, we have like this standardization of what the backends receive, like how we write down the circuit, and this is exactly where it's important actually, because for changing backends, all you need to do is change this little module, this part is standardized. It's like you take AND, OR, XOR, like assert 0 in this format, and this is very easy to integrate. And then there's like a little bit of initialization code for the prover and the verifier for example, if you have an interactive proof system, then here maybe you need to just open a session or something. So it's really easy to integrate backends, and we've gotten good feedback on that. Yeah, so there's some other benefits that come from having the Rust. So for one thing, that the binary that we have is something that generates the circuit, and it is not the circuit itself. And that's because the circuits themselves are massive. Like James mentioned, they're like in the millions and billions, like they're gigantic. You don't want to share them, but you can share something that generates the circuit. And another thing is that you can change parameters that would change the shape of the circuit or the size of the circuit, but you don't have to redeploy. So for example, with the medical check use case, you can add and remove disqualifying conditions or new healthcare providers, and you don't need to redeploy. You can just add them to the parameters. And another cute thing is that we just have WASM, and that's really nice. In our integration with backends, that's actually something we used. So we had an integration with our colleagues at Galois, and we did an integration where the backend that we used was their diet mac and cheese. And there we used a prover that was in WASM, so it was running on a phone, and it was interfacing with a server that was just in x86. And we also have just the textual backend as well, so that's the standardized format, and then we have integration with Emp Toolkit as well. So yeah, I'm excited to see how we can add some backends and new use cases. So if you have any ideas about that, please come talk to me, and that is everything for me. Thank you.
Okay, we have time for probably just one question. Anyone got any questions? Okay, one from me. Which proving system are you targeting with this DSL?
Sorry, can you repeat that?
Which proving system are you targeting with this DSL?
None, actually. Like we're not fixed on a specific proof system.
Okay, let me
right?
rephrase.
We're
Are you going for
we're generating
R1CS,
like a
or are you going for Plonkish? Or?
We give a representation of the circuit, right? There is a standard for representing the circuit where just like an arithmetic circuit, and we just spit that out.
So you're working directly with arithmetic circuits?
Yes. And we can just kind of skip that circuit generation when we have backends where we just feed it. We'll just have like direct bindings, right, awesome. To the backend.
Thank you for clearing that up. Can we thank the speaker again?